Professor Martha White, who's a professor in computer science here at IU. She did her bachelor's and PhD work at the University of Alberta. I think her bachelor's degree is in double majoring in both math and computer science, and the PhD she finished in 2014. And I saw recently you won an award for the best PhD thesis, and she's also won several other awards at big conferences like ICML, Best Paper Award, and things like that. So really happy that you agreed to give a talk, and really looking forward to it. Thanks so much.
Thanks, David. Okay, great. Well, I'm really excited to be here to tell you guys about reinforcement learning because I want more people to work on reinforcement learning. So this is partially, I'm really excited about this project. I think there's lots of things to do next, and it's also partially a pitch. So I'm going to tell you, before I tell you what I mean by sample efficient reinforcement learning, I'm going to tell you what some of my alternative purposes for this talk are. So I already told you I want to entice you about reinforcement learning. Reinforcement learning isn't as widely known as some of the other topics in machine learning, so I kind of want to give you a crash course on what it's about. And then hopefully you might consider taking my course called Stochastic Optimization in Machine Learning. And right now it's called In Machine Learning, but it's mostly going to be for online learning and reinforcement learning, which are both settings where you're taking actions and you're getting in observations in a streaming setting. So this course, some of the stuff I'll talk to you about today with gradient descent and reinforcement learning is really a lot of what that course is going to be based on. So you'll see if you're kind of interested in that topic. Though somewhat unrelated, I should mention that there's a colloquium this Friday with someone who works in reinforcement learning. He's a really engaging speaker. He's an entertaining guy, so you should definitely go to that colloquium. One other thing, this talk is also based on a paper that I have up on my website, and the course, all the course information is publicly available. You can just go to Canvas, you can look at the syllabus, and you can also see if you find the course interesting that way. Okay, great. So let me tell you what is reinforcement learning, and then I can tell you a little bit about what this talk is going to be about. Okay, so the general reinforcement learning setting is you have an agent, you have an environment, and you're going to have that agent interacting with that environment. So the agent's going to take actions, and on each step when it takes an action, it's going to get back the next state in the world and some reward that is telling you whether that action was a good action or whether it was a bad action. Okay, and then the agent's going to transition to that new state, it's going to get to take an action again, and this is going to be a repetitive loop. So because robots are fun, I'll just give a little small example with a robot. So imagine you have a robot and its actions are that it has to drive around in a room. Well, let's say it has a particularly difficult room to drive around. This is kind of hard to see, but it's a picture of a grad office that's extremely messy and difficult to navigate. So imagine you have this robot and you want it to try to navigate through this difficult environment. And maybe one of your goals is for it to deliver coffee to all of your graduate students. So you want it to be able to go through here and successfully deliver coffee. So you can imagine that it's going to take some actions. Now let's say it's in the state of the environment where it's at the door. So that could be one state, or it could be in other parts of the room that would define what state of the world it is in. Okay, so let's say it's going to take some action from that state. Let's say one action it could take is to actually hand the coffee to someone. This robot has hands, I suppose, that could actually hand coffee off. And so it's going to transition to the state where it has handed the coffee to someone, and it's going to receive some reward for doing that. So that was a good thing to do. It might get something like a +1 for having done that. Another action it could take is to throw the coffee on the ground or to drop the coffee. That would have been a bad thing to do, and it might get a reward like -10. So I'm simplifying dynamics that are somewhat complicated where you have an agent that has continuous actions and there's also continuous state. But this is the general idea where there's an agent that's constantly interacting. Okay, so there's two real main problem settings in reinforcement learning, two questions that we often want to ask. There's usually a prediction question and there's a control question. And the prediction question is usually going to be useful for the control question. So the control question is kind of what I've already described. We want to learn some policy that's going to do a good job, or it's going to do what we would like it to do. So it's going to take actions and it's going to get lots of reward. And lots of reward means it's doing what we would like it to do. Okay, as a subset of this control problem, or even just as it's on its own interest, you often have a prediction question, which is, given I had some hard-coded policy for this agent, let's imagine that someone, engineer, really sat down and thought of a good policy for an agent. We want to know what is the value of that policy. So if I let it loose in the environment, how much reward would it receive? Okay, so this is usually a useful thing to have inside the control algorithm, because the control algorithm will have some current policy, some way of deciding how it's going to take actions. And then it wants to know how good that policy is. If it could evaluate how good that policy is, it then can make it easier to decide how to change that policy. It can reevaluate that new policy, and then so on. It can start increasing the value. So the prediction question and the control question are somewhat related, but they're really the two main problem settings. In this talk, I'm mostly going to be talking about the prediction question first. because it is kind of the first step to getting towards the control question. Okay, so let me give you a couple examples of how the prediction and control question might work together, and also introduce one of the benchmark domains that is often used in reinforcement learning, and on which I'm going to show you experimental results later. So it's a nice little simple domain that tries to get across, or tries to solve some of the problems in reinforcement learning. So here we have this little car, and the goal for this car is to drive up to the top of this hill. So the goal is at the top of the hill. You get -1 reward per each step, and once you get to the goal, you finally get a reward of +1. So you really want to get to that goal at the top of the hill, and the longer you take to get there, the more negative reward you're getting, and the less happy you are. So you're getting punished constantly until you get to the top there. Okay, so this car, you can't just drive it right up the hill. It's underpowered. You have to rock back and forth. So this domain was introduced with the goal, trying to encapsulate the types of domains where you have to actually go further away from the goal to finally actually reach the goal. So one of the simplest ways you could try to define such a domain. Okay, one of the nice things that has continuous state, so rather than having a tabular setting, we want to start looking at continuous state information. So the state information is your position and your velocity. And you have 3 discrete actions. You can either accelerate forward, you can accelerate backward, or you can take the no action. You could also make the actions continuous, but a lot of reinforcement learning still deals with discrete actions. So we're going to stick with the discrete action case. Okay, so here, this prediction question, you might imagine you have some simple policy. Let's say you think you know how you can get the agent out of this valley, which you probably could. It's a pretty simple problem. But one really simple policy is just to do an energy pumping policy. So if you're already moving forward, continue to accelerate forward. If you're already moving backwards, choose to accelerate backwards. So you could say, that's my policy. I'm always going to take actions according to that policy. And then you might want to know, how many steps is it going to take me to get to the goal? So this is what your prediction question might look like. So for that policy, from each position and velocity point, you want to know how many more steps it will take me to get to that goal. So that would be like a prediction question. So you're not changing the policy, you're not improving the policy, you're just asking, how well does this policy do? How many negative steps is it going to have until it gets to the goal? Okay, and then of course you can do the next step, which is to do control. So you could approximate, let's say you started with this worse policy than the one that I showed you before. You could initialize with some policy, you could evaluate how good it is, and then you could start to modify your policy to actually improve this prediction. So here, on each of these different iterations, there's an underlying part that's predicting how good that policy is, then there's a policy improvement step, and then progressively this policy gets better and better and better. Okay, so that's how the prediction part is going to be used for control. But I'm not going to focus too much on control. This talk is really about the prediction question. All right. So what is the prediction question actually answering? I said we're making a prediction about rewards. Go ahead.
Can you just go back to a slide?
Yes.
These are policies, right?
So actually, this is one policy, and it's telling you what the value of that policy is. So if you took that policy and you started in position 0.5 with velocity 0.7, then it would take this many steps to get to the goal. So let's say you started up here where it actually takes a few steps.
This is the value of the policy.
It's the value of the policy.
But I can't read off what the policy is.
No, you cannot read off of the policy. So this is already obfuscated what the policy is. You have the policy underneath in some way that you've represented. In this case, it's a very easy if statement. If this, then do this. If this, then do that. There will be when you actually do the control question, there'll be other ways to represent the policy. There's also these things called action value. But anyway, there's a way to represent the policy. So that value function, which I plotted right there, is defined in a specific way. And this is the thing that we're going to be trying to predict in reinforcement learning, and then I'm going to tell you the objective value or the error function we're going to write down to obtain this value function, the way that we're going to predict this. Okay, so our goal is to predict something that looks like this. So this looks a little bit like the machine learning setting that you might be used to, so I'll explain specific cases. So our goal here is to say from a given state, so for example, if we're in position 0.5 with velocity 0.07, if we were to follow the policy from this state, so we were to take whatever action the policy says, this tells us what reward we are going to receive into the future, discounted by some gamma. So if gamma was 1, for example, you're just summing up all the rewards you're going to see into the future, and you're saying that that's what your value is. If gamma is 0, then you're just saying that my value is exactly the next reward that I'm going to see. Any gammas in between 0 and 1 are going to tell you how much you care about what your value is into the future. Okay, so for the gamma 0 setting, it kind of looks a little bit like a more typical machine learning setting where you are in some state where you might have some information about that state, and then you want to predict something that immediately occurs. This other setting where we're trying to predict rewards all the way into the future complicates matters a little bit because we don't have access to all that information in the future, and we can't really wait 10, 20, 50 steps. We want to try to update our values a little bit more incrementally. So I'm going to tell you how we're going to do that, but generally this is the goal that we're trying to do. We're trying to approximate this expected sum of returns, rewards all the way into the future. Okay, and one way that the first question we have to ask is how are we going to try to approximate this function? So this is a function of state. A common thing to do is to represent this function as a linear approximation. So if you've heard of linear regression for machine learning, this is essentially what we're doing here, but our target is just a little bit more complicated. So we might have some features here, x of s. So we're assuming that the environment hasn't necessarily given us the state itself, but they give us some observations or sensor readings that we get to have some information about what state we're in. So this is some features or attributes that you will get on this current time step. And W is the weights we're going to learn to linearly weight all those features. Okay, so in the mountain car setting, for example, if you had a real situation where you had a car on a road and it was trying to drive up, the features it might get, even though you know the position and velocity of that vehicle, it might only get features that are an image of what you can see outside the windshield. So the underlying state is there, but you might not have access to. You have a different type of information that gives you some insight of what that state might be. But in general, this is how we're going to approximate our value function. So here again, if we set gamma to 0, then we could try to learn some weights on these features to predict the next reward that we're immediately going to get. We could just take pairs of these features and the target reward, and we could do something like linear regression, try to approximate that. For general gamma, where we have discounting into the future, we're going to do something else, and our objective is going to look different. But still, you can kind of see how it's related to machine learning setting, the regular machine learning setting. Okay, so here's the objective that we're going to optimize. This is called the mean squared projected Bellman error, and let me tell you some of the components to this. I'm not going to exactly derive where this comes from, but you're going to just trust me that this is the right objective, and then we're going to talk about how we're going to optimize this objective. Okay, so these are probably the two most important parts of this objective. This is the temporal difference error, which is telling you this is what your prediction of your returns into the future are. So remember, this W is our current parameters. This is the features. And here we have the reward we received, and the thing that we're predicting is going to happen into the future on the next step. So this is like an approximation to what we're going to see into the future, and this is the thing that we actually predicted. So the temporal difference is giving you some notion of how incorrect your current estimate is. Okay, and then this eligibility trace, I'm just going to tell you, summarizes a bunch of information so that you can actually call back useful information about what actually happened in the future. So instead of waiting 10 steps, what you do is at your current step, you call back a bunch of information into the past. And it was almost like you waited that 10th step. So it's a clever way to try to send back information. Okay, at this point, I'm just going to take a quick pause. Can everyone see everything well? Is there any issues with how loud I'm speaking or anything? Okay, good. Okay, so these expectations, one lesson that's probably the most important is we're going to be seeing a bunch of feature vectors, and these expectations as defined here are according to the stationary distribution for the Markov chain induced by your policy. So if you know what that is, you'll be happy the expectations make sense. If you don't, it doesn't really matter. You can think of these expectations as all the samples we're going to see, what is the expected value of your temporal difference times that eligibility trace. And then here we have this covariance matrix of your features. Okay, so this is what our objective value is going to look like. And if we try to minimize this objective value and get the optimal W, then we're actually going to be getting the best. We're going to get a good approximation to our value function as a linear value function approximation. Okay, so what are the algorithms that actually try to do this? I'm going to tell you there's two main classes, and I'm going to try to do something that's a little bit more in between.
Can I ask?
Yes.
I'm still wondering about this equation of the optimization.
Yep.
There's some expectations there over parameters I don't understand. So I'm kind of worried that I'll get lost. So what exactly are these parameters?
Okay, so I guess maybe one thing I mentioned that these matrices are going to come into play. So that's one thing is that in the end, this objective value is going to look like trying to solve a linear system of equations in some way, where this A matrix defines your system in a useful way and this B matrix defines your system in a useful way. This part is the covariance matrix of your features. So this is the features that you'll actually see weighted according to your stationary distribution. And mu, yeah, so I really should have maybe explained that one. Imagine mu is pi in this case. Is the policy. It's the policy you're actually sampling from. Okay, now this temporal difference here is essentially giving you a measure of your error. So if you didn't have this part in the middle, you could almost just imagine it's a squared error term where your temporal difference encapsulates what your error is. It's slightly complicated by the fact that we're sending back all this information, but otherwise it's just an error term. Okay, good clarification. Okay, so there's really two main classes of functions that are going to optimize this objective. So we've seen the objective, we really know that we want to optimize this objective, and there's a quadratic batch, so an expensive but sample efficient way to solve this objective, and a more inefficient but takes longer to converge way to solve this. So temporal difference learning is one of the main algorithms, or one of the traditional algorithms for solving this problem. And really just samples this temporal difference. So you're going to take a sample with one state, and we're going to just step in the direction of that. So you can kind of think of it as a gradient, stochastic gradient descent approach. I don't want to lie to you and tell you that it actually is. Temporal difference learning is not actually a stochastic gradient descent approach, but it's almost a stochastic gradient descent approach. And lately, other algorithms have been introduced that really are true stochastic gradient descent approaches. But the motivation is very similar. So we're going to take a step in the direction of our gradient, and we're going to update our W progressively with one sample at a time. So on each step, that's only going to take us order D, where D is the number of features. So it's a linear time algorithm, but it's stochastic. We're only using samples. The least squares temporal difference algorithm is going to save a bunch of information in a big A matrix. And in order to store this A matrix, this thing is going to be a D by D. So I'm calling it a quadratic algorithm, which is going to take a lot more time to run than the temporal difference learning algorithm, but is a lot more sample efficient because we're actually saving all that information in a matrix and solving our system on each time. Okay, so there's these two classes of algorithms, and there's some algorithms that have been developed somewhat in between, but there are a lot fewer algorithms that are in between this expensive but very sample efficient and inexpensive but not sample efficient at all. So we really want to try to get the best of both worlds. Can we be more sample efficient but still be computationally efficient like TD? So that's really what the purpose of this talk is. I'm going to introduce a new class of algorithms that's going to try to help bridge this gap a little bit, both from the side of the LSTD methods and from the side of the TD methods. And it's going to be based on trying to incrementally approximate this matrix A, but doing it in a much more efficient way. So it's going to be nice and simple, and I think it's very elegant. Then I'll tell you a little bit about what a bias variance bound for this approximation. Then finally, I'll show you some experiments showing that the approximation is probably a good idea for the reinforced learning domains and the utility of one of these algorithms. Okay, good. Let's go back to optimizing the objective, and then it's going to be clear about where we can actually do this in between the TD methods and the batch methods. Okay, so I've already written out what this mean-square projected Bellman error is, and we can rewrite it solely in terms of matrices, and we're going to end up solving a linear system. So this is, again, one of those things where you're going to have to trust me that you can do this. So let me write out what these A matrices look like. We have this objective value here. If we take the gradient of this objective value with respect to W, we're actually going to get that it is equal to this product of matrices. So here we have an A matrix that is ordered D by D. We have a covariance matrix, and then we have this B vector, and we're trying to learn W. Okay, so as usual, when we take the gradient of an objective, we're going to set that gradient to 0, and we're going to try to solve for our parameters W. Here the solution is pretty clear. We're going to usually assume that these matrices are non-singular. We're going to bring them to one side, and then LSTD is going to solve this system of equations where the solution is just W is equal to A inverse times B. So I hope you can see that from here where we have just this regular systems of equations. So if we had access to A and if we had access to B, we could just go ahead and solve directly and get a closed form solution to our mean-square projected Bellman error. Okay, so these A matrices and B matrices are well defined as this expected value. So in practice, of course, we're going to have to build up approximations to this A matrix and the B vector using samples as we gather samples. So this is a streaming setting. We're constantly gathering new samples. And so on each time step, we're going to see some eligibility trace vector that I defined earlier, and we're going to see these features, so the difference between features on two time steps. This is how we can incrementally update on our average for A. So the true A is the expected value of this outer product of vectors. So we're just getting a sample average, and B, again, is just a sample average of what its expected value is supposed to be. So very basic LSTD algorithm. You're just incrementally doing a sample average, and then we're going to want to do a W is equal to A inverse B. Okay, so we have this D by D matrix. Doing an inverse is not going to be computationally efficient, so in practice there's actually a more efficient way to update the inverse instead of updating A and then taking the inverse. But In general, this is going to be an order d squared computation and order d squared storage per step, which maybe, I mean, polynomial is often what an algorithm, we want an algorithm to be, but for reinforcement learning, this is typically just too slow. Order, if you have 10,000, 1 million features, this becomes prohibitively expensive. Okay, and on the other end, we have the TD methods that are going to try to do this in a sample efficient way. And here, instead of rewriting everything in terms of matrices and then trying to solve the system of matrices, a common approach is try to sample our objective. So actually sample the gradient of our objective. So if you, I should actually just quickly look back here. If you look at what the gradient of our objective is, it has products of expectations in them. So when it comes to the gradient TD approaches, trying to sample our gradient is going to be problematic because we have products of expectations, and so we're not going to be able to get an unbiased sample of our gradient. So there's a strategy for trying to approximate how we're going to sample this gradient. I'm mostly going to just talk about LSTD today, how we're going to approximate the A matrix and then get a more efficient LSTD algorithm. But I just want to mention that from the other direction, you can also look at this objective, and you can use similar approximations to A to also get now a better or faster gradient TD algorithm. So it's going to be useful at combating this problem from both sides, whether starting from LSTD and making it more efficient, or starting from gradient TD and making it more sample efficient. So I'm going to be talking about this one, but in the course we'll also be talking a lot about this one. So that's mostly why I'm mentioning it, just so you know that there's this other class of things we'll look at. So in general, our goal is if we actually had some kind of efficient way to incrementally approximate A with reduced storage, then we could still do our nice W is equal to A inverse B, but it might be a lot more practical now than order D squared time and space. So how are we going to approximate A efficiently? Well, the first problem we have to tackle is how are we going to reduce the storage? Order D squared storage is a lot of space. So let's say we have some parameter R. We know we want to reduce that second D to be something less. So we're going to pick some parameter R, and we want to have storage order DR instead. So one option is to try to find some approximation AR to our matrix A that is dimension D times R, or that we can store efficiently in DR. Actually, I'll show you how we're going to store this efficiently in DR. But if anything that we're going to store in dimension DR is going to have to be at most rank R. It's going to be something that's going to be restricted. So we can imagine we want to find the closest rank R approximation to our original matrix A. And nicely, there's a known solution to this problem, and it's going to be related to the singular value decomposition. And in the end, we're going to end up storing this reduced storage singular value decomposition. So the singular value decomposition for a matrix A looks like a U sigma V transpose. So you can take any matrix, you can decompose it into a singular value decomposition. There's nothing special about our A matrix. And here we're going to have this U and V are orthonormal matrices, and sigma is a diagonal matrix of singular values. So the singular value decomposition for a matrix is really just saying you can decompose a matrix into a rotation, then you're going to do some scaling with your singular values in a diagonal, and then you're going to do a rotation again. In general, this decomposition is just useful for lots of things. For us, it's going to be useful for storing A in a different way, but I'll show you other reasons why singular value decomposition is useful. So it's going to be useful storing the singular value decomposition of A rather than A itself. Okay, so if you had this singular value decomposition, no approximation yet, the truncated singular value decomposition would be what our solution AR would be. That would be the optimal solution to that, finding the rank R A matrix that's the closest to our A matrix. And so this truncated singular value decomposition is just take your singular values, you have a diagonal matrix of singular values, that's D by D, and now just keep the top R singular values. Drop all the smallest singular values. Okay, when you drop all the smallest singular values, you're setting those to 0, and that corresponds to taking the first R columns of U, the first R columns of V, and of course just that first R diagonal of sigma. So now we have this AR, which is represented by U times a sigma times a V transpose, and this is a D by R, this is a D by R, and this is an R by R. Oh, so we're going to have we're only going to have DR storage. And we're going to have a matrix that presumably, as long as R is not too small, actually approximates A reasonably well. Okay. So yeah, there's some nice properties of trying to approximate A, or trying to represent A in this way. So we're going to have reduced storage. There's also lots of algorithms actually for incrementally approximating the singular value decomposition of a matrix. So we're going to want to do everything incrementally. We're going to take advantage of those algorithms. Another nice thing is there's been other approaches for actually making A smaller, one of those being just randomly subselecting features and having a reduced A matrix, an entire reduced A matrix. I like this approach because we're explicitly saying we have all these singular values that might actually be pretty small, so why don't we throw away parts of the space that we already know aren't influencing us very much. So those small singular values don't affect our solution very much, and so we're directing our approximation to the part of the system that we know should have the least effect. And the final last thing is that having our A matrix in a singular value decomposition lets us take advantage of some of these useful properties of orthonormal matrices. So one of these is that it'll be really easy to compute the inverse of our A matrix now. Because our inverse actually just looks just like this, where we only take the inverse of our singular values, and the U and the V are orthonormal matrices. They just stay there on the outside. I could write why that's the inverse, but I think I won't. If someone wants to know the answer to that question, I can tell you. I think a lot of people in this room know a lot about the singular value decomposition already anyway. Okay, one other thing I will mention you can kind of look, I wanted to put this here so you can see what the difference of these two solutions look like. So this is the W with the original A, and this is the W with our new rank R A. Okay, so here I just put rank of A because the rank of A might actually be less than D already, so some of the singular values might already be 0. But you can just imagine this is D. And so the solution looks like this system, and you can see when you have really small singular values, it's actually going to shoot up some of those values. And in this one where we have a rank R approximation, we're only summing up to the rth singular value. And as the singular values get smaller, we're dividing by a smaller number, and so we're going to get a larger inverse. So as long as R is somewhat smaller, we're only going to be dividing by numbers that are a little bit larger, and we're not going to have some instability issues that we might have had in the original W. So it's an additional benefit that we might actually want R to be less than D anyway, because we want to have nice, stable, regularized solutions. Okay, but then the next case is that, of course, if we pick R very small, we are going to have an approximation. We need to understand what kind of approximation we have. So if we picked R extremely small, let's say we picked R is equal to 1, we're clearly introducing some kind of bias. And we want to try to understand when picking smaller R is acceptable and how much bias we're going to introduce. Okay, so there's some cases where we might expect small R to be okay. One of those is, like I've already mentioned, if A already has some small singular values, we really do want to set R to be small enough to cut off some of those small singular values. Another case is if we had a lot of redundant or nearly dependent features. So it is something of a common approach in reinforcement learning and other machine learning settings to just generate lots of features and then hope that your algorithm can deal with all those features, because you don't want to have to carefully engineer features. So actually, I would say especially in reinforcement learning, this is a common strategy. So that we can at least hope that this is a little bit true, that there really will be redundant or nearly dependent features. And the last setting you might expect R to be small to be okay is if you have an agent that's only exploring a small part of the space. So you can imagine you would have an agent that goes through just say one part of the room, and all the features that describe that other part of the room are never really activated, and you're never seeing them in your A matrix. So it's like they were 0, or you anticipate that they are going to be 0. So that whole part of your space in your A matrix would actually have no information, and you really could truncate all that information away. Okay, so those are really the settings I expect R to be small to be okay. Okay, so we can say what we expect to happen. Of course, I'm going to run experiments also and show you what the A matrix look like. But I want to show you this nice bias variance trade-off theorem for this type of regularization. There's already some understanding of what our bias variance trade-off is for other types of regularization in reinforcement learning. So this new type of regularization has a bound that looks a little bit like this. Okay, so I just posted this here. I can tell some people are reading it, so I'm just going to give you 30 seconds to read it. Okay, I think that's 30 seconds. Okay, so let me just tell you a little bit about what some of this is saying. So this WTR is after seeing T samples, and you pick your rank R singular value decomposition, so your truncated R singular value decomposition solution, so right here, and you compare it to what the optimal W is if you had all the samples, so you actually converge to the optimal W. so not related to T or R in any way, then it can be bounded this way. And so this is saying this is the difference between what your non-truncated solution would be. So if you used all of your A matrix, and this part is telling you a little bit about what the bias of that approximation is. Okay, and this part is also a little bit related to bias, but this epsilon t, I'm expecting you to go to 0 pretty quickly. So both of these terms, as t goes to infinity, are going to decrease to 0. And this last term, even as t goes to infinity, is not going to decrease to 0. That's going to be the bias that we incur even after we converge. Okay, so one nice thing is, I'll mention a couple nice things. So let me see if there's something I've failed to mention in here. I don't think so. One nice thing is in this first part of the bound, a common thing to have in your bound is if you introduce some kind of approximation, having this difference here about what would be the optimal thing you could do at time step t. So this is the best thing that you could do. And here now we have this inverse relationship to your current singular value. So in some of the previous bounds that don't truncate those small singular values, this inverse relationship is actually more related to the smallest singular value, which could be very small. So here in our case, sigma r, depending on how you choose r, could actually be larger, and that part of the bound is going to be more reasonable. And the other thing here is that this part of this bias term also kind of clearly indicates how much bias we're incurring. I mean, it's a very intuitive part of the bound. If r was equal to d, we would have no bias. This part would disappear. And as r gets smaller and smaller, our singular values are getting larger and larger because the singular values are ordered from sigma 1 being the largest all the way up to the sigma d being the smallest. So of course this bias term is getting larger. Is there anything else I want to say here? No, I don't think so. Okay, so this gives us some intuition about, we should expect to incur some bias of this approximation, but we're hoping that along the way we'll actually have a more stable solution because of this better relationship to our singular values. Okay, so now I'm going to finally tell you how we're actually going to do this algorithm, how we're going to incrementally approximate this matrix. So the incremental approximation is really just going to take advantage of a well-known incremental SVD algorithm. And so I just want to mention to you a little bit what this incremental SVD algorithm looks like, and then I'll show you specifically how it looks for the reinforced learning case. Okay, so the incremental SVD algorithm works like this. You assume for your current step, you have your singular value decomposition, and now you want to incorporate some new data and update that singular value decomposition. That's what you do for an incremental SVD. Okay, so we know for our A matrix, we're always going to be taking our current A, and we're going to be adding this new outer product of vectors. If you remember, our A was the sample average, so on each step, we're always adding a new thing to our sample average. Okay, so we're going to add this term to our sample average, and now we want to update this singular value decomposition of the A we had on the previous step with all the new information that we're getting. And this information is just rank 1 information. It's just the outer product of two vectors. Okay, let me think about how I'm going to go through this algorithm. So the generic form of this algorithm is you assume you have some matrix X and you have some new information A and B. And this, in our case, like I wrote here, the A is just a vector ET, and B is DT. So actually, I kind of wanted to go through this algorithm just to show you how simple it is to do an incremental SVD. Once you have your SVD, getting the next SVD, just adding this information is pretty simple. So here we have the original U and V, and you can just rewrite what this sum is. This is really just algebraically writing out what is happening here. Okay, so this first term, we have an orthonormal matrix, and we have this A now, which is not orthonormal. So we want to make sure we get our new U on this side that's, again, orthonormal. So we have our SVDs. So here we can break up this UA into a U times a P, where this P is orthonormal. So that's going to be our new U that we care about. And we have this other matrix. Okay, so the P is an orthogonal basis for this matrix here. And so we can break up UA into the product of these two matrices. And you can do the same thing for the VB transpose. It's symmetric in that way. And we're going to have a Q for this V and a similar matrix that looks like this. Okay, so now our matrix, this UP is going to be our new U, or is going to be part of our new U. That's still an orthonormal matrix. On the other side where we have V, we're going to have a VQ that's also going to be orthonormal. And we're left with these extra matrices that have some new information that are neither diagonal nor are they orthonormal. So we have to do something with them. Okay, so these are going to be producted both from the U side and from the V side, and we're going to have this inner matrix. So we're going to have UP times K and then times VQ transpose. So all we really need to do is take this matrix do an SVD of that matrix. In fact, maybe I'll just write it down. All we need to do is take an SVD of this K matrix, and we have this on one side, we have UP. I'm going to call this a UV prime. And we have on the other side VQ transpose. And now this is an orthonormal matrix. If we product by another orthonormal matrix, this thing is still going to be orthonormal. This is going to be our new U. This sigma is a diagonal matrix, so it's going to be our new sigma. I'll call that prime as well. And then on this side, we're going to have our V prime transpose. So this is going to be our new V. Okay, so just very simple algebraic steps to try to figure out what our incremental SVD would be. That is the summary of that algorithm. There are other algorithms that do slightly different things, but most of them are going to involve similar algebraic steps. Okay, continuing. Okay, so let me tell you how this is going to look like for the TLSC algorithm then. Where this update SVD is exactly what I just described to you, but this is looking at what a reinforcement learning loop might look like. Okay, so we're going to initialize our values to be empty because we have no information about our system yet. And then just to show you a little bit what the reinforcement learning setting looks like, we're going to repeat this loop where the agent is interacting with the environment. So we have this agent environment loop. So we're going to take action according to pi. We're going to observe some new next state information. So we are currently in state x. We transition into some new state x prime. And we're going to receive some reward for taking that action. We're going to compute these two vectors that are going to be added to our A matrix when we do our update to A. And we increment our B also, which is just a sample average. B was always a vector. We never really had to worry about approximating B. That was always efficient to maintain. Okay, and then once we gather that information, we're going to pass this off to our update SVD algorithm. We're going to update the SVD for our A matrix. And then at the end, we're going to use the nice properties of pseudo-inverse for our A matrix, where we just have to invert the values in our sigma, and we get to product by our orthonormal matrices. If you just carefully product these things where you do a U transpose B first, that's always going to be order dr, and then you're always going to be producting a matrix and a vector, and you're keeping all your computations at order dr to compute your W. So this is the part that is really going to matter, is how we're going to do our update SVD. In the experiments I'm going to show you, you could either do a batch setting or you could do a fully incremental update. So here, for example, if you picked a mini batch of K, you're going to gather more samples, and you're actually going to build up an A matrix and a B matrix where you store more information than just one Z and D. Or if you had this mini batch of size K equal to 1, then you would just have the fully incremental setting. So let me just tell you about those two algorithms. The mini batch setting is kind of nice just because by doing a little bit of mini batching, so having a mini batch of size R, you get to amortize some of your complexity, and you can get a fully ordered dr algorithm. The fully incremental case, where k is equal to 1, we have ordered dr plus r cubed. So as your r gets a little bit larger, that r cubed starts to become problematic. I know there are ways to reduce that r cubed, and I'm excited to try to find those ways, but the mini match does give you a way to take advantage of that fact. Okay, so this mini batch algorithm I've already kind of described is really exactly what I described here. We're just going to pass in the information we've stored in Z and D. So Z and D are incorporating all the last Z and Ds we saw in our time steps. And then we just apply this incremental update algorithm. We're going to find our orthogonal bases, QZ and QD. We're going to compute this K. We're going to get the SVD of the K, and we're just going to update our U and our V. So all these steps are going to take order dr squared. If we do it in a mini batch of R, it amortizes over R steps, so we get a nice order dr algorithm. Okay, good. So the incremental one looks a lot more crazy. I only have so much time, so I'm not going to go through exactly what happens here. There are a few nice steps. Is there anything I want to highlight particularly? No. But if you ever want to think about how you could make this algorithm faster, if you are like me and love trying to make algorithms faster, the part that is preventing this algorithm from being faster than order dr plus r cubed, this r cubed is messing things up, is this matrix multiplication between our r by r matrix L and the new r by r matrix that we get from this diagonalization of K. So if you love matrix multiplication and you know how to make that faster, you should tell me. Okay, I'm going to continue. So this incremental update is also similarly nice. And so we'll end up with our final TLSC algorithm, where you can either do your update with mini batches, you can also do it fully incrementally. You know, order dr plus r cubed is still a lot better than what we had before, especially because we're typically going to want to pick r to be reasonably small. In the experiments that I'll show you, it's for domains where we didn't even try to find a domain where we thought we would have nice redundant features, and still it gave us some useful speed-ups. Okay, so generally the pluses for this algorithm is that we can now efficiently store these matrices. We have a more efficient algorithm. And in general, these truncated updates have been shown to be effective in practice. So one thing I haven't really told you about yet is that incremental SVD algorithm that I showed you assumed you always kept the previous SVD of A and you added in whatever information you wanted. When you add in this new information, it can actually increase your rank beyond the rank that you really want to have. So you could have an R, and then you'd have R plus 1, R plus 2. Eventually, you might actually get your rank all the way up to the rank, some larger rank that is unacceptable to you. So the incremental SVD algorithms are assuming you allow the rank to actually increase if it needs to increase. But we are, very storage and computation constrained. We want to make sure we actually truncate it at each step. And surprisingly, despite how widely that is used, where you take this incremental SVD and then you truncate it, no one has yet to prove that this is actually going to converge and that it's a valid way to do an incremental SVD. So this is one really big open question for this TLSD algorithm. I mean, in practice, almost everyone reports that they find convergence under truncation, and similarly, we find the same thing, but it's clearly an important open question. Okay, so now let me tell you a little bit about the experimental results. So we just want to find out what this looks like, what keeping a singular-value decomposition of our A matrix looks like in some of the most simple settings in reinforcement learning that are very commonly explored. So though it may be surprising, looking at a lower rank approximation of the A matrix just hasn't been done in reinforcement learning before, mostly because these highly expensive computations with the A matrix, if you're doing those computations, then you're happy just to have order D squared, and otherwise it's completely unacceptable and you're just using temporal difference learning algorithms. So there hasn't been as much effort in the middle, and so there's a lot less understanding about what that looks like. So we're going to start in two settings that are very well known, mountain car and pendulum, two very simple benchmark tasks. And we're going to look at two different representations that are also very widely used, tile coding and radial basis functions. So the first thing we're going to ask is, what are the properties of the A matrix? So can we actually hope to do well, or is the A matrix going to be completely full rank with lots of really large singular values? And then afterwards, what's the performance of this new algorithm? Okay, so I've already told you what mountain car is, so I'm just going to remind you this is what mountain car is. Okay, and the other domain we looked at is pendulum. Another nice simple benchmark task where the goal is that you have this pendulum, just remind you what a pendulum is in case you forgot. The goal is you also have actions right, left, and no action, and your goal is to right up the pendulum, so you get to push it back and forth until you get it up, and it has to be able to stay up for a small amount of time, and then it can drop again. So that is the goal for this task, encoded with physics, dynamics, and so on. So there's specific settings for how heavy the pendulum was. I'm not going to go through all those specific settings. Okay, so for the two representations, the radial basis functions are popular in reinforcement learning. They're popular in machine learning. They're just popular. So this is one of the things that we used. So just to give you a little understanding of how this will work for this domain, our original I shouldn't have called this X. This should be called S. X is going to be this new representation we have. So imagine this is S. This is our position and our velocity. And now the features we're going to have are these radial basis features. Radial basis functions are you take some input. Here our input's going to be some two-dimensional vector, and you're going to compare it to many different centers that you have chosen. So here we're going to select a set of centers CI. And so this is what this looks like right here. We have some inputs. They're going to be input into each of these different functions. And each of these functions is defined by center. So here we are going to choose P centers. And this new feature just tells us how similar it is to this center. So we're converting our original features into similarity features. And so you imagine you would want to pick your centers so they're somewhat distinct from each other, and you'll only ever be similar to a few of the centers, and most of the centers you won't be similar to. So that value will be somewhat close to 0. Usually we add in some kind of bias unit, so you can always approximate a mean. And now our value function approximation just looks like learning the weight, so it's still a linear value function approximation, but this is the features that we're actually going to be looking at. Okay, so the center selection question, typically in reinforcement learning, you're just going to take a grid and you're going to cover your space in some kind of uniform way. We didn't select our centers in any more clever way than that. Okay. And the other type of representation, which is very popular in reinforcement learning, is actually somewhat similar to radial basis functions. It's just a bit more of a discrete version of radial basis functions. But you may not actually have heard of tile coding before. You've probably heard of radial basis function networks, but maybe not tile coding. So the idea is similar. We still have this 2D space, so we have some point in this space. And now we're going to discretize across our continuous values, but we're going to discretize with multiple tilings that overlap. So we're not just discretizing. We're getting some generalization by having tilings. So here, for example, we could discretize this space into this 4x4 grid. And now you would have 4 times 4 features. So we have 16 features, and you would have 1 if it was in that grid and 0 everywhere else, because it's not in any of the other grids. So that would be your first 16 features. And then you could have another overlapping tiling. So here, for example, tiling 1 is this blue tiling. And then you might shift your tiling down and discretize your space a little differently. So your discretization is going to be different for the second tiling. The first tiling maybe went 0, 1, 1, 2, 3, 4, 4, 5. And the second one, maybe you'll do minus 0.5 to 0.5, 0.5 to 1.5. So you're just going to shift your tilings. Okay, so you'll get another set of 16 features, and this point is only going to have 1, 1 in that set of 16 and 0 everywhere else, because it can only be in one of these grids. So as you add more and more tilings, here there's 4, you'll have 4 features that are 1 and everything else 0. If you had 8 tilings, you'd have 8 features that are 1, and so on. You can see kind of like the radial basis function networks, you're going to have local features that are telling you how close you are to other points. And having these additional tilings lets you generalize a little bit. You'll be similar to some points and similar to other points in different ways. Okay, so those are the main things. Okay, I should hurry up because I don't want to keep you guys here too long. So the first thing that's interesting is that the properties of our A matrix, actually, they're the properties that we would hope for. The singular values are quite small after an initial amount. So here there's a dimension of, we had 100 RBFs, so radial basis functions, and 1,000 tile coding features. And for the RBFs, it's already at 20 features, 20 singular values. You pretty much have all the rest of the singular values being equal to 0. So you can really truncate all those values. You're unlikely to affect the solution of your system that much. Somewhat unsurprisingly, tile coding requires actually more singular values to represent it. That's something I actually somewhat expected, and it definitely translates into the results, where TLSTD works better for the RBF case than it does for the tile coding case. The other thing that you might find interesting is that as the width of your RBF increases, then you get kind of more redundancy in your features, and again, fewer singular values are required to actually approximate your A matrix. So, of course, the RBFs, it is going to be highly dependent on how you pick those widths. So, first result, we can be somewhat confident that maybe our algorithm could do something. If we saw a line up here that stayed quite high for most of the time, it would be much less likely we could do something useful. Although even then, you might imagine approximation could still do well. They are somewhat separate questions. Okay, so now the last thing to show is just what does the learning curves actually look like. So because I have little time, I'm just going to give you the highlight of what can be drawn from this. The first thing is that as you make R smaller, you can clearly see that there is bias introduced. So especially here for the tile coding representation, it's not doing that well for R is equal to 30. So here we have 1,000 features. If we pick R is equal to 30, which is a lot less than 100, we get really good early learning performance, which is nice, but then it levels off because of that bias and doesn't improve from there. If we increase R to be 100, then we actually maintain better performance. So this blue line is TD. That's the thing we're trying to be more sample efficient than, but it's going to be more computationally efficient than us. And this light blue line is LSTD, which is more sample efficient than us, but is always going to be more computationally expensive. So we're expecting to be between these lines in some way, especially for early learning. I mean, that's kind of what we're seeing. Yeah, that's kind of what we're seeing. So the results are a little bit nicer for RBFs, where even for something as small as R is equal to 30, we're getting nice performance. We're doing almost as well as LSTD, which is the best thing that you could hope to do for these domains, but with much less computation. But there's still clearly something to be understood for how much the bias is influencing, what other domains we could actually get more gain here. I mean, my opinion is that R is equal to 100 is just too big. We want to have R smaller than that. Okay, and one other thing, this kind of shows you a little bit about the fact that this algorithm is actually converging as well. So if you were to give it 2,000 samples, 5,000 samples, 10,000 samples, how is the performance compared to LSTD as you allow the rank to increase? So this is assuming you do the truncated algorithm along the way, and you can kind of see the impact of rank. This really mirrors the previous results. You know, the tile coding one, it requires higher rank. For RBFs, it requires lower rank. Okay. And this graph will take a little longer to explain. So I'm just going to skip it. I'm going to tell you the main conclusion, which is that TLSTD gets most of the same runtime performance as TD does. So it gains a lot of the sample efficiency of LSTD without, and it gains a lot of the sample efficiency of LSTD, but runs almost as fast as TD in terms of learning. That one's going to take too long to explain. Okay, so the main conclusions then. It seems to be a lot of promise in trying to introduce approximations to this A matrix. So this was one way we were able to approximate the A matrix more efficiently. You can imagine lots of other ways to approximate this A matrix. So it seems to me a great way to try to improve the sample efficiency of our methods, but also significantly reduce computation, and really kind of try to toggle between the two. I think it's a little bit surprising, actually, that we found that A had so many small singular values. It's both surprising and nice, particularly because those are representations that are typically used in RL. And I'm really excited about exploring this new class of algorithms. One thing I'll mention is there's lots of new steps. Some of these new steps are the ones I hope to explore in the course with all of you guys. Things are like improved approximations to A. Can we get convergence results for this incremental SVD? I didn't mention this ATD algorithm, which is taking this A approximation, but coming from the TD side rather than the LSTD side. And there's lots of really cool accelerations you can do there, too, with stochastic gradient descent. So I think this is going to be really cool. And last thing is the results kind of suggested that you could also use this TLSD for early learning and then switch to TD, and you can maybe get the best of both worlds. So that's another question I really want to ask. And finally, of course, other domains. There's lots of robotics domains out there where you really have lots of redundant sensors, and I think this will actually show a lot more promise in a domain where it's really clear that we're going to have those redundant features. All right. Thank you very much. Yeah, go ahead, Michael.
So, is the effect of approximating A in terms of the optimization algorithm that you're just choosing a descent direction as opposed to the direction of steepest descent? And the idea is if you have a good approximation, then you ought to have a descent direction that's nearly the steepest direction.
So, sorry, the first part of your question was, is the idea of using A for the ATD side or also for TLSTD?
I don't
Okay.
know. I haven't assimilated enough of the
Okay.
presentation
Yeah.
to respond to that.
Okay, so the question, I think, is the idea that having some kind of an approximation to this A matrix would at least give you a descent direction, even if it isn't the steepest descent direction.
Correct.
So for the LSTD case, since we're resolving the entire system each time, I mean, I suppose that could be thought of like a gradient descent approach, but I have never really thought of it that way. So the answer on the LSTD side is maybe, if I could think of it like gradient descent. On the other side, if we were to use this for the gradient version of this, the ATD one, where we're not resolving the system, but rather we're taking a step in the direction of the gradient with that approximate A, I think there the answer would be something like yes, probably. That this approximate A would be like having approximate Hessian, like you have for quasi-Newton methods, and so it would give you a reasonable step in the direction of gradient, but would be the best one.
So if that's the case, then since we know that often we can be better in optimization by not doing all the work to find the best descent direction, merely working less, then presumably and especially since you say empirically you see gains even in situations where you've got where your singular value structure wouldn't necessarily predict it, would it not make sense then to, rather than doing a full decomposition and truncating, just say, I'm just going to take the first 5, which would presumably result in tremendous algorithmic savings because you're only finding a fixed number of singular vectors instead of trying to do the whole thing.
So definitely part of this incremental algorithm was that when we do the truncation, on each step you'd only add one new rank in. So most you could increase your rank by 1. So let's say to R plus 1, and it would always truncate back to R. So it would never be doing the entire singular value decomposition.
Okay.
But I do agree with you that for this incremental case, R equal to 5 even might work perfectly well because an approximation for the ATD case I think is actually going to work a lot better than for the LSTD case. Where the LSTD case we're actually resolving the entire system, the accuracy of this A matters a lot more than if you're just taking a step in the direction of a gradient.
Okay.
with this approximate A. Yeah, so I'm really excited about that one, actually.
Right.
Yeah, go ahead, Teja.
Okay, I don't know exactly what I'm asking, but I think it seems to me that this could be another way. I don't know whether there's any work on that, as you know, I'm not an expert, but it seems like maybe ideas of sketching could be applicable to speeding up these algorithms. Approximating this inverse of A using a sketch A where you could compute faster. I mean, is that something that exists?
Because I also don't know exactly what sketching means, I think it means randomly, you pick random matrices and then you get reasonable approximations along the way, and then an expectation.
Random, but maybe you clip them or you
That's
do
true.
various types of
There's
things.
clever ways to
Yeah.
sketch. That's not just random. That's true.
Yeah.
So a lot of approaches right now do the random one where you can say at least an expectation it's going to do something reasonable. So I guess in some sense that's kind of like a sketching approach. But I haven't seen anyone doing more clever type of sketching. So that's a good idea.
You can say every value of A that is less than threshold T goes to 0. That can speed up a lot of computation. You know, you can use sparse inverse matrix. You want it to speed up that R squared, R cubed, right? But I don't know. You can invert the matrix in linear time if it's sparse, right? So suddenly those things can become completely different. Even you can speed up the original algorithm. I also don't remember the terminology, but the one A inverse B.
Yeah.
That can be sped up if you can sketch or whatever, do something with the.
I think that's a good idea. I mean, I'm not actually sure if A would be sparse. I was anticipating it would be low rank, but it could be sparse. Yeah, you're right. If you clipped it, it might be sparse. So that could be another approach. I agree. I'm not tied to this as approximating A. Any way to approximate A that's efficient would be nice. So I like that. Go ahead, Sriram.
So this is more high-level question. About LSTD, how sensitive it is to the choice of the underlying function approximation?
So how, when we go back to these, the actual LSTD itself. Let me think back to, for example, I can think back to how well it worked for different widths for the RBFs. I'm not sure how sensitive it's going to be. I mean, it is solving the system. As long as the A matrix is approximated reasonably well, it's almost always going to do a better job than TD. So in the same sense that TD will be sensitive to the function approximator, LSTD will also be sensitive to the function approximator. And I mean, it always matters a lot how good your function approximator is. In machine learning and reinforcement learning. So I'm not sure.
So because 10 years back, one of the reasons I gave up continuous RL was because we couldn't get TD to work with many of these function approximators. It was very sensitive to these parametric choices. It was the mountain kind of range.
Okay.
And actually one of my colleagues, Prof, in the end took that problem because I just said, no, I can't do it. It's too sensitive for me. But that was not LSTD. It was plain vanilla TD that we tried back then.
In fact, what I say about TD, LSTD is probably going to be easier to use because you get to have the whole batch of data. You're resolving a system. TD is compounded with sometimes your function approximator might not be good, and stochastic gradient descent can be really hard to tune the step sizes. So you may have found things like step sizes were really confusing you. If Adam here, for example, is an expert in reinforced learning. He is really good at making reinforced learning algorithms do cool things. So he will impart that knowledge upon everyone.
One more question.
Yeah.
Can I sit in your class?
Of course.
Just to follow up on Hedge's comment, in multidimensional scaling, there's a class of algorithms that are basically weighted gradient algorithms, and the computational bottleneck is computing a pseudo-inverse, so doing an SVD, although you can get around that a little bit. It turns out that you can replace the actual matrix that would give you the optimal descent direction with a diagonal matrix.
Okay.
So it's trivial to invert. So you've removed the computational bottleneck at the cost of suboptimal iterations. But the trade-off turns out to be very favorable, that you know, in terms of total expense of doing some finite number of iterations, you really gain by doing that. So, you know, it may be that whatever the structure of the actual matrices may be, that there would be tremendous gains to insisting that you're going to approximate them with a sparse matrix of some sort, even if that's not the kind of matrix you have. You
Right.
there may be gains in doing that.
Yeah, that sounds cool. I'm going to look into that paper. Okay, I've kept you guys here long enough, so I'm going to let you go.